In this session, we're going to explore inverses of exponential functions. Recall that if we have a function f that maps elements from its domain into its range, then its inverse acts in reverse, right? It maps elements from the range of f, which then becomes the domain of f inverse, into the domain of f, which then becomes the range of f inverse. When we consider a function that's exponential, say f of x is equal to, for instance, 2 to the x, remember that the domain of f is a bunch of exponents, and the range of f I'm going to call results. Therefore, when we look at the inverse of f inverse, it's going to take in results and spit out exponents. So when we look at the inverse of an exponential function, what we're really looking at as an output is, what is the exponent? So in short, we can say that the inverse of a function reverses inputs and outputs. Or if you like, it reverses the domain and the range. Or we could say it reverses x's and y's. And these things are important to understand, inverses in general and exponential functions inverses in particular. With this in mind, we move on to our first example. Analyze and graph f inverse for f of x is equal to 2 to the x. What I first want to do is look at an xy table. I know, I always do that, don't I? But it's because I think it's beneficial. An xy table where we're going to put in numbers that are going to become exponents, right? Because the domain of an exponential function is the exponent. So -3, -2, -1, 0, 1, 2, and 3 are good inputs. The outputs that we get for that, 1/8, 1/4, 1/2, 1, 2, 4, and 8. Now that's for the function f of x. What we want to consider is f inverse. And since the inverse of a function switches inputs and outputs, x's and y's, all we need to do is reverse the ordered pairs represented. So 1/8, 1/4, 1/2. 1/8 will map to -3. 1/4 will map to -2. And so on, up to 4 mapping to 2 and 8 mapping to 3. Keep in mind that the inputs for f were exponents, which means that the outputs for f inverse are exponents. It's very important to keep that in mind. Now, what I'm going to do is we're going to draw the graph of f of x equals 2 to the x, but we're going to use a dashed line to do so. So let me get that down by first plotting my points and then drawing that exponential curve that's asymptotic with the x-axis on the left and sweeps up to the right. We can write down a couple of things about f, namely its domain is, of course, the set of all real numbers, because any number can be an exponent. Its range is the set of positive numbers, 0 to infinity, because of that horizontal asymptote, which I'm also going to write down. The horizontal asymptote is, of course, y is equal to 0. And then finally, we have a y-intercept of 0, 1. That's indicated in our xy table. And I notice I left out that ordered pair in my xy table for f inverse, so I'm going to throw that in here, 1, 0, because that's actually kind of important to me. Now, you may remember that the graph of an inverse of a function is a reflection about the line y equals x. We're going to see how that plays out here, but really what we're going to do is we're going to plot the ordered pairs in the table that we generated for f inverse. So let me go ahead and do that. And then connect those dots with a nice smooth curve. Notice it's kind of bending up to the right in the first quadrant, and then it becomes asymptotic with the y-axis down there. We had a y-intercept for f, and that was the point 0, 1. That point for the inverse becomes the point 1, 0, right, switching x's and y's. And so we have an x-intercept there. That's a key, to me, to remembering how the shape of the graph of this inverse goes. Now, for the analysis portion, we can say that the domain and range are related to those of the original function. Remember that the domain and ranges switch. And so where the range of f is 0 to infinity, the domain of the inverse is going to be 0 to infinity. Likewise, the domain of the original is the set of real numbers, and the range of the inverse is the set of real numbers. If we consider the horizontal asymptote that we had, y equals 0, and the fact that inverses switch x and y's, then we end up with a vertical asymptote for the inverse, and its equation is going to be x equals 0. And so let's feature that on the graph. It's the y-axis, and as we see, the graph is asymptotic down with the y-axis. Finally, in the original function, we had a y-intercept of 0, 1. That's going to switch for the inverse to becoming an x-intercept of 1, 0. And that's, of course, featured in the graph as well. So for analyze, we're looking at domain, range, asymptote, and intercept where possible, where we can do that. And the red function is our inverse. Now that it seems that we kind of hopefully understand the inverse, let's think more about generating some values. In other words, I'm going to put a number down, 16, in the xy table for the inverse. This is f inverse, remember. Let's go back and look. F itself is 2 to the x. So the inverse is asking, what's the exponent that will give me the result of, in this case, 16? That's what this table represents, generally speaking. In other words, if we look at f first, then the 2, 4 entry, when x is 2, y is 4, that means the exponent of 2 on 2 gives us 4. If we look at 3, 8, that means that the exponent 3 on the base 2 gives us 8, right? That's the meaning of these things. So when we look at f inverses table, when we look at the x value of 8, we're asking what's the exponent on 2 that'll give us 8? The answer is 3. So now we're looking at what's the exponent on 2 that'll give us 16? The answer is 4. What's the exponent on 2 that gives us 32? And the answer is going to be 5. So we're looking at what is the exponent in each case. Let's write that down. F inverse is asking what is the exponent. And if it seems like I'm driving this into the ground, it's because I am, but it's also because I want you to thoroughly know that you understand this right now. You get that the inverse is asking what's the exponent. And so on your notes right now, I want you to write down, yes, I get this. Yeah, I know. Just do it. Okay, check this out. For the function f of x is equal to 2 to the x, the inverse function, f inverse of x, is what we call log base 2 of x. It's a logarithm. You see, a logarithm is simply an exponent. Nothing more, nothing less. A logarithm is an exponent. And so, when we look at, say, f inverse of 16, we're looking at log base 2 of 16, and it's nothing more and nothing less than asking, what's the exponent on the base 2 that gives us 16? Answer being 4. All right, so now that the cat's out of the bag on that one, let's analyze and graph the function g of x is equal to log base 1/2 of x. First, we ask ourselves, what's the base? Well, it's that little subscript 1/2. What I think of when I try to analyze a logarithmic function is I think of an exponential function. And so I'm thinking of y equals 1/2 to the x. I think of how x and y values would go for that first. So if x is -2 as an exponent on 1/2, that's going to give us a 4. If x is -1, we get a 2. If the exponent is 0, we get a 1. If the exponent is 1, we get the base, 1/2. And if the exponent is 2, then we get 1/4. That's for y equals 1/2 to the x. This g of x is the inverse of the exponential. And so what we want to do is reverse the x and y table. I think that's the easiest way to understand what's going on with these. And so 4 maps to -2, 2 to -1, 1 to 0, 1/2 to 1, and 1/4 to 2. Now we're going to plot these points and then connect them with a nice smooth curve. Looks like it's going to be asymptotic up on the y-axis and then curve down. We see that there's a vertical asymptote, and that's going to be characteristic of logarithmic functions. We can also see about the domain. So let me write some of that stuff down. The domain is the set of positive numbers. And that's evident in the graph where we are asymptotic just to the right of the y-axis. And it indicates that what you put into a logarithmic function can't be 0 or negative. And so we're actually going to write down right now that x has to be positive. The argument of a logarithmic function must be positive. And when we say argument, what we're saying is what we're finding the logarithm of. In this case, that's the domain. And you see that's related to the range of an exponential function. And if the base is positive, the outputs will always be positive. So when we switch this around, the inputs of a log must always be positive. The range, all real numbers. As stated, we have a vertical asymptote that is the y-axis, and so x equals 0. And then we have a, not a y-intercept, but an x-intercept of 1, 0. There's our analysis. There's our graph. Next, we're going to look at analyze and graph the function h of x is equal to log base 3 of x minus 2 plus 1, x minus 2 being the argument. Let's start this one looking at the domain. For the domain, we need x minus 2 to be positive, as we just discussed. And so x has to be greater than 2, solving that inequality. We can wrap a set notation around that and say it's the set of x such that x is greater than 2, or we could give that an interval notation, a parenthesis 2 comma infinity. I don't really care which one you give me. But that number there is going to indicate our vertical asymptote. As you recall, if we have a number that's being subtracted or added to an argument, then that indicates a horizontal translation. In this case, since it's x minus 2, it's to the right 2. For the plus 1 that's outside of the argument, that's a vertical translation, in this case, up 1. I remember that there is a vertical asymptote, and so like I said, that's kind of obtained from the domain. In our last two examples, the vertical asymptote was the y-axis. In this case, we have a horizontal translation to the right, and so that vertical asymptote moves to the right by 2 units. So I'm going to draw that vertical asymptote. But then let's look at the function y equals 3 to the x. Why 3 to the x? Because of that question, what's the base? In this case, for log base 3, the base is 3. Looking at the xy table for y equals 3 to the x, I would have values for input -2, I'm going to get 1/9. For an input of -1, I'm going to get 1/3. For an input of 0, I'm going to get 1. And 1 will become 3. And 2 will map to 9. That's for y equals 3 to the x, the exponential function. The reason I care about that is because the logarithmic function is the inverse. If I switch the x and y values, then I have ordered pairs 1/9, -2, 1/3, -1, etc. And if I plot those, then I get an indication of the shape that I'm trying to draw. And then we go for the horizontal and vertical translation. And so each of these points that I plotted is going to get moved to the right by 2 units and up 1 unit. Drawing the resulting curve gives me a logarithmic function that has been moved up 1 unit and to the right by 2 units. I don't think that you need to do all of that for every graph. Here's what I like to do. I like to think of where the point 1, 0 goes, remembering that that comes from switching 0, 1 for an exponential function. If I know where the point 1, 0 is going to go, in this case, to the right 2 units and then up 1 unit, and where the vertical asymptote lands, then I just flesh out the rest of the graph. That seems to work for me. As far as the analysis here, as we wrote down, I'm just going to write it down again to consolidate it. I don't want a scavenger hunt, so it'd be nice if you consolidated it all for me on, say, an exam. Domain 2 to infinity. The range is, of course, all real numbers. We have a vertical asymptote of x is equal to 2. And the x-intercept is actually a little bit tricky, and so we're actually going to hold off on exploring that. I want to talk a little bit about the vertical asymptote. Notice we wrote down the equation x is equal to 2. And sometimes folks will write down just a number for an asymptote. They'll say the asymptote is 2 or 0 or -1 or something. But notice that in the case of, say, an exponential function, we have a horizontal asymptote that would have an equation y equals some number. Here we have a vertical asymptote, x equals, in this case, 2. It's not sufficient to just say it's 2. You've got to tell me, using the equation, whether it's a horizontal or a vertical asymptote. And so make sure you do that, number one. Number two, on a test, when I ask for the domain, range, and asymptotes of logarithmic functions, a lot of times folks will give me 2 asymptotes. They'll give me a horizontal and a vertical. The exponential functions have a horizontal asymptote. The logarithmic functions have a vertical asymptote. In these contexts, folks, no graph has both a horizontal and a vertical asymptote. That occurs with other functions, but it does not occur with exponential and logarithmic functions. Now we're going to take a moment to consider some special bases. First, a non-special one. If we have a function f of x, which equals 2 to the x, then what we've been looking at is the inverse. F inverse of x is equal to log base 2 of x. In other words, the subscript indicates the base. If, though, we have a function, say g of x is equal to 10 to the x, then its inverse, g inverse of x, is log of x. In other words, if the base is not written in the logarithmic function, then the base is understood to be 10. And log x, or log, is a button in your calculator. It indicates a base of 10. If we have a function, say h of x is equal to e to the x, that is if the base is e, Euler's number, then our inverse, h inverse of x, is going to equal the ln of x, which I do not like. Don't be lazy. It's the natural log of x, but I said ln, so you know what to write. And again, if we have an ln, natural logarithm, then the base is Euler's number, e. The one that's written log with the base of 10 is called the common log. and the one that's ln x, natural log. It's called the natural log. And that's because basically it shows up in nature. So just to be like abundantly clear, you won't see really log base e of x. If the base is e, then it's written using ln, which, by the way, is also a button in your scientific calculator. And since e is approximately 2.718, it's important to note that it is greater than 1, which actually makes a difference as far as the exponential curves. It makes a difference for the logarithmic curves, as you saw when the base was 1/2 a couple of examples ago. Now we have that under our belt, what we can do is now analyze and graph the function y equals the natural log of x. We could look at this from an xy table point of view, try to put in, say, -1, 0, 1, 2, etc. Might be good to put e into this. And what you would find if you grabbed your calculator is -1 has no output. It'll give you error. 0 will give you an error as well. 1 is going to give you an output of 0. 2 is going to give you something like 0.69. If you could put e into your calculator, it would give you an answer of 1. And then 3 is going to map to something like 1.1. These are tricky to try to plot, but I wouldn't really plot these. What I would do is I would think about the exponential curve that I know exists and is related to base of e, and then reflect it about the line y equals x, which is kind of what I do in my head anyway. And I know that the exponential curve would have a y-intercept of 0, 1, so the logarithmic curve has an x-intercept of 1, 0. The exponential curve would have a horizontal asymptote of y equals 0. The logarithmic curve has a vertical asymptote of x equals 0. And then the shape of a logarithmic curve is asymptotic in the lower y-axis and then bends up and to the right. And this is going to be characteristic as long as the base is bigger than 1, which it is in the case of the natural log because the base is e. In the case where we had y is equal to log base 1/2 of x a few minutes ago, we had a graph that was asymptotic up in the y-axis and then curved down and to the right. That's going to happen whenever the base is between 0 and 1. We don't consider a negative base for the same reasons that we discussed with the exponential stuff. So we have two curves that are logarithmic. One of them is asymptotic up, the other is asymptotic down with the y-axis. And what indicates which of these you have is the base, whether it's bigger than or less than 1, noting that all bases are positive. Well, the rest of the analysis here is going to consist of the domain, the range, and in this case, the vertical asymptote. And I know that the domain is 0 to infinity. The range is all real numbers. And of course, the vertical asymptote in this case is x is equal to 0. Because it's easy to see, I'm going to include the x-intercept, which is of course the point 1, 0. Now on to our next example. Analyze and graph the function f of x is equal to 4 minus the log of x plus 6. This looks a little bit weird to me. I'm going to rearrange the terms. I'm going to rewrite this as f of x is equal to negative log of x plus 6 plus 4. And now it's probably a little bit clearer to see. We have a horizontal translation to the left of 6 units. That was probably easy to see to begin with. But we have a vertical translation up 4 units. It just was a little bit disturbing the way it was written. Furthermore, because the logarithmic term is negative, we have a reflection. It's upside down. What's the base? The base is 10. And I know that because it doesn't have a base written. And so we could think about y equals 10 to the x and generating an xy table. If we did, we would have something like -1 maps to 1/10, 0 maps to 1, and 1 maps to 10, and reverse those points and then apply the transformations. But I'd rather think about the shape and where to put it. So we have that vertical translation of up 4 units, and the horizontal translation to the left of 6 units. I'm going to deal with the horizontal one first. That's going to tell me where to put the asymptote, which in this case is x equals -6. And then I've noticed that the graphs we've been drawing have had an x-intercept that was 1 unit away from the asymptote. If I know where that x-intercept is going to land, then I have a pretty good idea how to draw this graph. In this case, the x-intercept lands up 4 units. And so I'm drawing a curve that is asymptotic with the line x equals -6, and then bends up to the right. But this actually isn't right because we have that reflection. And so it's actually going to come from the top, asymptotic with the line x equals -6, and then bend to the right. And you're going to say, wait a minute, that was a different base. Well, this one's been reflected, and so we have to take that into account. In any case, now we have this shape, which is a logarithmic curve. It's been reflected vertically, that is, it's upside down. It's been shifted to the left by 6 units. It's been shifted up by 4 units. And that's how I would like for you to draw a curve like this. We were asked to analyze. Recall that as far as the domain, the argument has to be positive. So in this case, x plus 6 has to be greater than 0. Solving this, I get x is greater than -6, at which point you might say, wait a minute, x has to be positive. That's not true. The argument has to be positive. I can put in a negative number provided that I'm not finding the log of a negative number. What we have in this case is that the domain is -6 to infinity. The range is, as usual for logarithmic functions, all real numbers. And then we have the vertical asymptote of x equals -6. I'm not going to bother with the x-intercept or the y-intercept for that matter. One of them involves solving a logarithmic equation. We don't know how to do that yet. And the other one is a detail that I don't really want you to have to worry about right now.